everyone. Thank you for this wonderful opportunity. I'm Srija Chakraborty and I'm a PhD student at Scuola Normale Superiore, and today I'd like to say a few words about my work on probing supermassive black holes with LISA. I'm working under the supervision of Dr. Simona Gallerani, and we tried to understand the gravitational wave signals we would expect to detect through the Laser Interferometer Space Antenna, or LISA for high redshift massive black hole binaries coalescence, and the possibility of detection of electromagnetic counterparts of the host galaxies of such massive black hole binary mergers. We are interested in the formation and evolution of massive black holes in early universe, and this study could provide a deeper understanding in such. This brings us to the mysterious growth of supermassive black holes and why are we interested in it. Black hole mass measurement through reverberation mapping in quasars around redshift 6 shows that the mass of such black holes can reach up to 2 times 10 to the power 9 solar masses in less than 0.7 gigayears, which is astounding to ponder how such massive black holes can exist in such a young universe. There are many models to explain the formation of such massive black holes. One of the most popular among astrophysicists is the direct collapse black hole scenario. The idea is that primordial gas collapses without fragmentation, so in a metal-free environment with a typical virial temperature above 10 to the power 4 Kelvin, to not form molecular hydrogen and sufficiently large Lyman-Warner photon flux to destroy molecular hydrogen, because molecular hydrogen efficiently cools the gas and can cause fragmentation, which is what we don't want. So such fragment-free primordial gas collapse gives rise to heavy seeds of massive black holes around 10 to the power 5 to 10 to the power 6 solar masses, which can then grow to the observed mass by merging and accretion. So we use zoom-in simulations, Gadget 3, to track simulated massive black holes growth by merging through their gravitational wave signals and accretion. We use two different feedback models where feedback is a fraction of the energy accreted by the black hole, which is radiated away and coupled to the surrounding gas. We consider two resolutions of simulations, one comoving kiloparsecs based on the work of Barai 2018, representing kinetic feedback where the feedback couples kinetically through energy-driven winds in the surrounding media, in either a spherical geometry or a biconical geometry with the black hole at the apex, and secondly a resolution of 0.5 comoving kiloparsecs as used by Valentini 2021, which is still under preparation, where the AGN feedback couples thermally and isotropically to the surrounding gas. What happens in the simulation is first, a dark matter only low resolution simulation is carried out in a simulation box, which is evolved from redshift 100 to redshift 6 using periodic boundary conditions. The most massive halo is then chosen at redshift 6 and resimulated with a higher resolution or zoomed in. Here you can see the merger rates predicted by each simulation for each feedback model considered plotted with respect to redshift. Different resolutions and feedback can be differentiated based on the merger rates of the model. In these feedback models, the merger rates depend on the relative distance of separation of the black holes as well as the sound speed of the surrounding medium of the black holes. In the AGNsphere feedback, the sound speed is higher and the black hole smoothing length is smaller as compared to the cone case, resulting in a high number of mergers in the AGNcone case. We compare our results in the chirpmass range less than 10 to the power 6 solar masses with renowned literature, Hartwig Aggarwal and Sana, where in Hartwig Aggarwal chunky simulation based on Ramsey's code is used, and we have compared our results with the critical Lyman-Warner flux associated with direct collapse black hole formation of 30 times 10 to the power minus 21 erg centimeters square per second per hertz per steradian, and for Susana we have considered two models of stellar feedback. The high feedback model with high star formation rate and hence rapid metal enrichment where the direct collapse black hole formation stops earlier, so around redshift 18, and low feedback model where the feedback is milder and the halos remain metal free for longer, so the direct collapse black hole formation stops around redshift 15. So we choose our fiducial case with the merger rate between these extremal values with optimistic Lyman-Warner flux. Here you can see the coalescence mass distribution with respect to the mass ratios of the massive black hole binaries in four feedback models. The white space in the bottom right represents the non-analyzed binaries due to our resolution limits, and on the top left, the white bins correspond to the binaries falling outside the detection window. In all cases, we see that the maximum number of events occurs for equimass binaries for low masses, so just seeded binaries have a higher probability of merging as compared to black holes which grow to higher mass through merging and accretion. The signal-to-noise ratio for the gravitational wave events are estimated through the classical Flanagan and Hughes formalism, keeping the threshold of detection by LISA at SNR equals to 10. We show a scatter map of the signal-to-noise ratio with respect to redshift and chirpmass, and we find the frequency of detection is inversely proportional to the mass of the system. So for higher mass spectrum, the merger gravitational wave frequency is lower, and from this SNR we calculate the angular resolution for the detectable events of a fiducial case to explore the possibility of complementary electromagnetic detection of the gravitational wave events. And on the left we see the fraction of events detectable by LISA for each feedback model. The detectable number is related directly to the mass distribution of the binaries in each feedback case, as I already explained before. From the angular resolutions, we see that we have better prospects of localizing our gravitational wave events for low mass binaries at lower redshifts, and this localization is important for other electromagnetic facilities to follow up the gravitational wave event, which brings us to the possibility of detection of gravitational wave events through electromagnetic counterparts post-merger. We use a distance threshold at each redshift bin for the coalescing binaries to associate them with a host galaxy and calculate the UV luminosity, which is the sum of the UV flux due to the star formation and AGN, the extra luminosity FIR and C+ luminosities for the host galaxies. These quantities give us information of star formation rate in the galaxies, the ISM properties, which can then be explored to detect post-merger galactic changes. In the movie, you can see a galactic merger occurring, and in our simulation models, central massive black holes merge upon galactic coalescence, and the new black hole is positioned at the center of the new galaxy. From all the events in our fiducial case, we select the events which are bright in different electromagnetic bands, by which I mean with an UV magnitude of at least -21, FIR luminosity greater than 10 to the power 12 times solar luminosity, and X-ray and C+ luminosity of at least 10 to the power 12 solar luminosity, and also with a detectable SNR in LISA. We select electromagnetic facilities which will be potential contemporaries of LISA and see that, especially for X-ray missions, the field of view is extremely small and we can only make follow-up observations upon precise localization of gravitational wave events. We also compared the range of sensitivities of different electromagnetic missions and compared it with the SAD of two electromagnetically bright and LISA detectable events, and see the potential of the events to be discovered by electromagnetic instruments such as ALMA, ATLAS, Origins, etc. And finally, we create UV FIR maps of the selected events from our simulations that we would expect to see through eligible telescopes and present a panoramic view of the gravitational wave event. To conclude, we saw that different AGN feedback channels can be differentiated in direct collapse black hole formation model from the merger rates of the massive black hole binaries. Now, keeping a threshold of signal-to-noise ratio 10, which is quite optimistic, we find angular resolution of most LISA events to be quite poor, but not out of reach. Upon relating with host galaxies of merger events and exploring possibility of different electromagnetic facilities to observe post-merger galaxy, we present a panoramic view of gravitational wave events and its post-merger scenario. And to summarize, gravitational wave detection with LISA from massive black hole binaries can create new pathways for cosmological knowledge, and including the electromagnetic counterparts observations would create a better understanding of our universe. Thank you for your time and attention.